The next topic I'm going to talk about is a very important topic that deals with angular momentum. You've done, you've learned linear momentum, and you know that how. What is the expression for linear momentum, by the way? And which symbol do we use that for? What is the symbol for linear momentum? Linear momentum, P, and how do we calculate that? mv, right? So let's say this is when you have a single particle that's moving with a velocity. It has a mass m, so your p is equal to mv, all right? And and we also mentioned that the Newton's second law can be described, as the time rate of change of linear momentum. So that's your dp dt, and that's also equal to your ma. And yesterday we mentioned that when you have a force, there's a counterpart, in rotation. Instead of using the force, we use a symbol, and that symbol is, what is a one-to-one, correspondence for, when you have an object that's in rotation? Force in linear motion, and then you have, not inertia. Didn't we just mention the quantity earlier? Torque, exactly. When you have force, then in rotation we have torque. So that's equal to something. So you can well imagine that it is equal to something or time rate of change. It's just that what is that thing? Okay, so that just keep it like that. And then that's equal to, so instead of ma, we have, instead of ma, in rotation we have, for mass we have I alpha, exactly. Okay, and the alpha of course comes with the direction as well. So you can see there's a one-on-one equivalency. Force is equivalent to torque in rotation, and then your mass is equivalent to rotation inertia in rotation, and your A is your alpha. Okay, so now the question is, we have a P, linear momentum. So you can bet that when you have an object that's rotation, there is another quantity that deals with momentum as well. And that momentum, we call that, what kind of momentum would that be? In rotation, we call that angular momentum, right? Everything is angular. So when you have rotation, you just put the angular velocity, angular velocity, angular acceleration, and angular momentum. And we use lowercase l to indicate that's angular momentum for a single particle. Okay? So this is angular momentum. So in that case, your L here, just by looking at this equation, what would that be? Your linear motion, you have mv. For rotation, your angular momentum would be, instead of mass, we should have something equivalent, right? So that will be rotation inertia, your I, and your, omega, exactly. Again, omega is a vector, so it comes with the direction. So your L is equal to I omega. The difference between these two expressions is that linear momentum is just in reference to the, your reference point, that's say, your Cartesian coordinate. And then when you have rotation inertia, you are specifying the angular momentum. It is about a rotation axis. So your rotation axis is the reference axis. So you have I omega, and then you have torque that's equal to I alpha. Okay. Now we also mentioned that force and torque are related to each other. So your force is equal to R cross, your torque. So I should write it here. So your torque is equal to R cross F. So this is torque that, that relates how the torque is produced by applied force. That's torque is equal to R cross F. So likewise, we can well imagine that the angular momentum and linear momentum, they have to be related to each other. How are they related to each other? So you will have this is R is what we call the moment arm, or the radius, where the force is applied. And then, so instead of accounting for the force, because you want to relate the angular momentum to linear momentum, so this will be your R cross P. Okay? So this is how we relate the angular momentum to linear momentum. That is just equal to R cross P. So so we mentioned that the magnitude would be that torque is equal to Rf and then sine of the angle between them. Likewise, whenever you have two vectors that do the cross product, the magnitude would just be Rp and then sine theta. Okay, so you have the magnitude-wise, you have this, that's Rf sine theta or Rp sine theta, and your P here, of course, in magnitude that would just mass times velocity. Okay, so in other words, you have two ways for torque. For torque, you can for torque there are two expressions. One is R cross F, and one is I alpha. Now for angular momentum, you also have two expressions. One is R cross P, and the other one is I omega. And you'll find that in several scenarios, you can have situations that initially the object the object has linear momentum, and that linear momentum is at a distance from the rotation axis, so it has an angular momentum. And then after through different processes, then the object is rotating and acquires angular velocity. So in those scenarios, you will have to utilize both both expressions. So in other words, your L comes with two expressions. One involves rotation inertia, and one involves the linear momentum. Okay. Likewise, your torque involves rotation inertia and the applied force. Okay. So in that case, what would be? By the way, did we mention about the unit for torque? We didn't, right? So what would be the unit for torque if we just look at this? What would be the unit for torque? You have R cross F, so meters and then times Newton, right? Okay, so m times Newton. That will be the unit for torque. What about angular momentum? For angular momentum, again, we're going to utilize this expression. It's equal to R cross P. So you will have meters times kilogram, and then meter per second. So you have meter squared, and then that, right? Okay, so this is a unit for angular momentum, that meter square kilogram per second, and this is meter times Newton. That will be the unit for torque. Okay, so you can see that this is when we're dealing with when you have a single particle, and that single particle is moving with a velocity, and that velocity and it carries a mass, so it has linear momentum. And if the momentum is moving, in reference to some distance away from the rotation axis, so it will have an angular momentum, and that angular momentum is R cross P. Okay. Now imagine that if you have a collection of particles in your system, how would you account for the total momentum, the total angular momentum of the system? Instead of just each single particle is going to have their own angular momentum. So how do we find the total angular momentum of the system? You just basically sum out all the individual ones, right? So in other words, the angular momentum of the system, when you have a collection of particles, we use capital L to indicate that's a total linear momentum of the system. And that would just be the summation, the vector summation of each individual angular momentum, and so forth. Okay? So that's simple enough. I mean, this is nothing new. Now, the last concept that we want to get to is the conservation of angular momentum. We mentioned that when you have an isolated system, when you have yes. Okay, just put it. Yeah. Okay. Put it in my office. I'll talk to you later. Okay. Sorry. All right, I don't know how to cut this, so I don't want to, do a lot of excessive, non-necessary things here. All right, so right, angular momentum. We mentioned that linear momentum is conserved, and it's a very powerful conservation law, because when you have an isolated system, everything is within the isolated system, the net force acting on the isolated system is zero. Then what quantity would not change? When the net force acting on within an isolated system is zero. And if you remember, when you have a system and this is a net force, that's equal to dp dt, the time rate change of linear momentum. If this is equal to this, okay? If this the net force acting on the system is 0, which means that the net force equals to 0. When you have a net force that equals to 0, which means that the time rate change of linear momentum has to be equal to 0. And under what condition would that be? That P is what would that be? When you do the time derivative of something and it doesn't change at all. It has to be a constant, right? So likewise, so that's why we say that when you have within an isolated system, when the net force acting on the system is 0, the linear momentum is a conserved quantity. In other words, what this means is that initial linear momentum has to be equal to the final linear momentum. During this initial state and the final state, there are processes that can transfer energy and momentum. But then you will find that after you sum up all the changes, you will still get the final linear momentum that has to be equal to the initial linear momentum. Okay, and so likewise, when you're dealing with something that's in rotation, similar law can be arrived as well, because we realize the net torque acting on an isolated system is also equal to the time rate of change of angular momentum. Okay, so if the net torque acting on the system is 0, it means that the angular momentum has to be a constant as well. If it's a constant, it means that the initial angular momentum and the final linear momentum, angular momentum, has to be equal to each other. Okay, so, and this is what we call the conservation of angular momentum, which is very powerful, and you'll find that there's a lot of applications by using the conservation of angular momentum. Okay, so in fact, I'm going to show you the one that demonstrates the conservation of angular momentum. So, all right. So I need somebody to bring down the projector screen. Dan, can you do that? Thank you. Is it on? Yeah. So I'm going to turn off lights so easier for you to see. So basically, you can see that conservation of angular momentum. That's a Earth. Earth is rotating, so it is a rotating object. So for a rotating object, you can imagine that there are ways to change its rotational rate. I mean, what is the period of the Earth's rotation? What is the period for the Earth making one revolution? Isn't that just a day? Yeah, 24 hours, right? So it's making a rotation that complete. It takes 24 hours to make a one complete revolution. So you can imagine that so from periods you can actually deduce the angular velocity, right? You said how do we relate t and omega? I think we went over that when you have a uniform circular motion, t and omega that relate to each other. That t is equal to 2 pi over omega, right? Yeah, I think that's correct formula. So, okay, so that's how you relate period and the angular velocity to each other. So based on that, you can actually calculate how fast the Earth is rotating. So imagine that. I mean, there was I don't know. I mean, several years ago, like a couple years ago, there was a big earthquake, and and then that earthquake, basically people was like kind of like suggesting that because the earthquake was so huge that it kind of redistribute some of the masses on the Earth, and if there's a redistribution, let's say in a very extreme cases, when you have a huge earthquake and the masses on Earth is actually redistributed around the globe, what kind of impact would you expect? So the mass itself still remain the same before and after the earthquake, right? It doesn't change. But then what will be changed if you have a mass redistributed around the sphere? You treat Earth. You can treat Earth as a solid sphere. Yes. The center mass changes, right? And also, what will be changed? Yes. The average radius, okay, so if, let's say, the average radius would change, and you remember, when you have a solid sphere, you have rotation inertia, right? And that's based on the uniform distribution of masses. Now you have a mass that's distributed differently, which means that rotation inertia will be the same or different. Your rotation inertia will actually be different when the masses are redistributed. Let's say some of the masses actually move to the other side, and so you have to actually reconfigure your rotation inertia. So in other words, before the earthquake, after the earthquake, your I changes. The rotation inertia changes. What is the implications of that when rotation inertia changes? Yeah. So in other words, the rotational rate of Earth will change as well, right? Because based on the conservation of angular momentum, the Li, which is I omega is equal to I omega. So your I now changes. Your omega has to change, correspondingly, so that those two quantities before and after the event, they will be equal to each other. So this is how the implication. So when people are talking about like distribution, the immediate thought that should come to you is that, okay, rotation inertia has to change, which means that it's going to affect the rotational rate of the Earth. And in fact, there's a problem that deal with if all the ice, if all the ice in the polar region melted, what kind of effect will they have on the Earth? Okay, so you can actually do it. I picked that problem because I thought that was kind of interesting, especially when we're dealing with the climate change and all that stuff. So it is a distinct possibility that the ice could melt completely. We don't know. So, but anyway, so I want to show you these pictures. You can see that this is a guy. The rotation. He is sitting on a chair and he has two dumbbells on his hand. And then, he's actually like doing this. So he's like, extending his arms away from his body and then pulling his arm, close to his body. And in the meantime, we give him an initial push, and it's going to rotate, right? So in that case, let's see, when he has arms extended away from him, as opposed when you have arms close to his body, which one will rotate fast? The one closer or the one that's away? Closer to his body. Why is that? When you have your mass that's close to the, that's more close to each other, which means that rotation inertia is smaller, okay? Because, when you have a mass that's distributed widely, then rotation inertia will be actually larger. So when you have a distribution, the mass distribution that's closer to each other, the rotational rate will be larger than compared to this case when you have mass that's distributed farther apart. So rotational inertia in this case will be a little bit larger. When I is larger, then your omega has to be slower, so that before and after they have to be equal to each other. So if one gets larger, one has to be smaller. Okay, and that's based on the conservation of an angular momentum. All right. So now we're going to actually do a very interesting demo, and I need a volunteer. And of course, that person has to sign the waiver as well. In fact, I'm going to have everyone sign. Who wants to come here and do it? And when you do this, it's actually, you have to be a little bit careful because, you can get very dizzy. Maybe we don't do this first. Let's just have one person stand on this, and then we'll have another student push that person to rotate, and then the person just going to extend the arms and pulling the arms, toward his body or her body, and just experience the difference. And we can actually see visually. Who wants to do it? Volunteer, you get bonus point. I need 2 volunteers. All right, so you too? Don't worry, we got plenty of, All right, so stand on it, and then you want to be a little bit careful. Let me just move this away. Yeah. Okay, so step on it. What you want to do is that, do it like that. And then just release your hands. And then you just like, and then slowly, now push her. Yeah. Okay, slowly extend, and then, yeah. Did you see the change of the rate? That when she extends her arm, she slows down, and when she pull her arms in, she can, yeah, yeah.
It's like ice skating.
Yeah, exactly. That's actually ice skating as well.
Yeah, ice skate.
Yeah.
Are we good?
Yeah, you're good. Okay. Now, do you want to do that?
Sure.
Are you strong enough to handle this?
Yeah, I think.
Okay, all right. Now I need another person to, so step on it.
Okay.
And you hold this. Oop. Okay, hold this. Hold the bars.
Okay.
Okay, what you want to do is, can you, okay. So what you want to do is that, that's it. If I spin it and you want to like slowly change this rotation.
Okay. So
Do,
like
yes,
that?
yeah, rotate, uh-huh.
Okay.
Mm-hmm, okay.
Oh.
Okay.
Change it?
Yeah, and then do the other way. You can see that when she, and then keep going, yeah. Okay, now change direction.
Wait, this?
Yeah, keep going. Uh-huh. You can see that when she changed directions, I mean, her body responding differently as well, right? Okay, just do one more, yeah.
This is fun.
Right? So she's like, exactly. And why is that? It's also based on the conservation of angular momentum, because when she turned around, the angular momentum changed sign, so that her body has to do the other way to counteract the changes. And this is how I think in satellite, not satellite, in space shuttle, they actually utilize this to correct its motions. Okay, so I think we'll